Now, this item B is intrinsic geometry, exterior algebra in 3 dimensions. This is B part 1, manifold. B part 1, lecture 3, manifold and tangent bundle. Now you see, a manifold, for who is, for instance, took classes in mechanical engineering, civil engineering, mathematics, and physics. This is intrinsic geometry. Looks strange, you see, because it's completely different from the calculus you have seen in the courses, the graduate course, and also in the undergraduate course. Okay, this is to understand. You have to go step by step, see, to grasp, okay, this new theory. Okay? Now, a manifold is a mathematical space that is locally similar to Euclidean space, but can have a more complex global structure. The key idea behind a manifold is that on a small scale it looks like R3 in the Euclidean space, but globally it may have curvature. You see, this is an example of a manifold, and the small scales looks like R3. And this is a tangent plane over here. This blue one is a tangent plane at point P of the manifold. Okay, that's written here. So M is the manifold. Okay, one important concept is all the points in the manifold, they are independent. Okay, that's a very, very fundamental, okay, concept. You see, each point of this manifold, okay, each point, it has its own tangent plane. And the set of all tangent planes are called tangent bundle. So tangent bundle. Now, for you to understand clearly why all these points over here, they are independent. You see, we will, in the next video, to derive a tangent plane at a certain point P of the manifold. You see, this is our next lecture. Okay, I'll derive this plane here. Attention now. That's important. This is a small scale that looks like the Euclidean space. See? Now, all of us, okay, mainly in the high school, we learn, okay, and we study. They call atlas. See? And then, an example that I'm giving here, you see, the next will be how to obtain the tangent plane TPI, since they are independent. That is an example which I said in the high school you use, okay, is this: each point on the map, when you open the map, the atlas, okay, is a plane. You see two variables. You see the latitude and longitude. You see, we call latitude and longitude a label for points on the Earth. Please concentrate what I'm saying. You see, you never sum or add latitude, longitude in one point plus latitude and longitude in another point. So there is, when you label all these points, you see it's meaningless to add what is happening, for instance, this point P1 to the point P2. You see? There is no position vector. Okay? There is no position vector. You just open the atlas, you see the page, you read latitude and longitude. So you mark a point on the Earth. Obviously, the radius is constant. Okay? This is the equator. You see, that's an example. The blue one, okay, is, in this case, is the latitude. Okay? In the case of the Earth, you have north latitude and south latitude. And the red one is the longitude. You see? So if you give the latitude north or south and longitude, you label a point, okay, for the Earth, which the radius r is constant. So this example tells you clearly that you cannot do anything when you have one point and its neighbor just to, for instance, if you mark a vector, okay, a distance vector, there is no vector, okay, no dot product. See, when you see the latitude and longitude at one point, if I ask you, okay, do the dot product, you can't, because these are labeler points. See, that's the first main idea, and unfortunately, in the many literature, you don't see this clearly. See, they say the points are independent. So we reinforce, okay, this idea, just what we learned in the high school, okay, on the Earth. That's now, the next video, I repeat, I will show how to obtain each of these tangent plane. Say each of them, they are independent. So remember that they are quite important because locally is similar to Euclidean space. There you can add dot product, cross product, because in the Euclidean space there is a vector over there. You can do, okay, with what you want to do, okay, because it's a point, okay, you work 2 points on this tangent plane, okay, but this tangent plane is an approximation, okay, of the curvature, okay, to this point here. The points on the tangent plane, they are an approximation, okay, of the points on the manifold. You see, if you have a curve over here, okay, if you have a plane over here, okay, if you work at the point of the plane here, so the points on this plane approximate in a small scale the points on the manifold. Okay, this approximation. That's the first important concept. What really is the intrinsic geometry? Okay, that's clear when you see this example, or I emphasize, okay, in this lecture. So prepare for the next lecture. Then we will construct tangent space, okay? Because there is an approximation, points on the small scale, close to the point of interest, point P, for instance, okay? Then we create this plane, okay? That's it.